Dear learner, welcome to Module 4, that is Wind Energy Technologies. Before learning about harnessing energy from any source, we should first get to know all about that source, about its nature and origin, the factors governing it, and all the possible variations which may occur due to time, place, or other factors. In today's lecture, we will learn about the basics of wind, its nature and origin, various types of wind, and other parameters. Wind is a natural phenomena that has shaped our world for ages. It is a vital component of the Earth's atmosphere system. Its nature and origin are interesting topics that involve a complex relationship of meteorological, geographical, and astronomical factors. Understanding the details of wind is crucial for various applications, including weather forecasting, renewable energy harnessing, and ecological studies. Now, what is wind? Wind is nothing but the movement of air in the Earth's atmosphere, mainly driven by differences in atmospheric pressure. Wind is caused by differences in air pressure. The sun heats the earth unevenly, causing differences in temperatures and pressure. This results in the movement of air from areas of high pressure to areas of the greater the pressure difference, the stronger the wind. Wind can occur at various scales from gentle breezes to powerful storms and cyclones. Just like we feel a breeze on our face when we walk or the wind blowing through our hair, the earth's experience winds on a much larger scale. Wind can be gentle like a soft breeze or strong like a gust during a storm. Understanding where wind comes from and how it behaves helps us predict weather, use it for energy, and even plan our outdoor activities. Now we will see the factors influencing wind. Several factors influence the generation and behavior of wind. The primary drivers include differential heating of the Earth's surface. Under this, unequal heating of the Earth's surface by the sun results in temperature variations and subsequently in pressure differences, initiating wind patterns. The sun is like the ultimate wind maker. It heats different parts of the earth at different rates, creating areas of high and low pressure. Next is rotation of the earth. Under this category, the earth's rotation influences wind patterns through the corollaries effect, determining the direction of the wind. Next one is topography. Mountains, valleys, and other geographical features can significantly impact wind patterns by causing local variations in pressure and air circulation. When air hits a mountain, it's forced to go up, creating wind patterns around the slopes. Next one is bodies of water. Large bodies of water, such as oceans and seas, can influence wind patterns by moderating temperatures and creating onshore and offshore breezes. Water and land heat up and cool down differently. So, if you are near the ocean, you might feel a nice sea breeze because the land heats up and cools down faster than the water. Now we will see the Coriolis effect. The Coriolis effect, a result of the Earth's rotation, plays a fundamental role in determining the direction of wind. As can be seen in the diagram, in the northern hemisphere, winds are deflected to the right, and in the southern hemisphere, they are deflected to the left. This deflection is why the trade winds prevailing westerlies and polar easterlies have distinct directions in the different hemispheres. Now we will discuss origin of wind. As we discussed earlier, the origin of wind can be tracked back to the sun, which serves as the ultimate source of energy. Solar radiation heats the earth unevenly, creating variation in temperature and pressure across the globe. As the sun heats the surface, warm air rises, creating a low pressure area. Cooler air then rushes in to fill this void, resulting in wind. Localized wind patterns such as sea breezes and land breezes are generated due to temperature differences between land and water. During the day, the land heats up faster than the adjacent water, causing the air to rise over the land and draw in cooler air from the sea, resulting in a sea breeze. At night, the land cools more quickly than the water, leading to a land bridge as the cooler air from the land moves toward the warmer water. So, dear learner, the nature and the origin of wind are intricately tied to the fundamental principle of atmospheric physics and the Earth's geological and geographical features. Understanding these factors is essential for predicting weather patterns, harnessing wind energy for sustainable power generation, and understanding the dynamics of our planet's incretic ecosystem. Wind, a powerful force of a nature, continues to shape the world we live in and holds immense potential for the future of sustainable energy and environmental preservation. Next, we will discuss the types of wind. The classification of wind is based on various factors such as its origin, speed, and geographical location. Understanding the different types of wind is a crucial for meteorologists, renewable energy developers, sailors, and environmentalists. Global wind energy system are large-scale patterns of air movement that circulate around the earth influenced by the earth's rotation and solar heating. These include first one is trade winds, second prevailing westerlies, and third is polar easterlies. So first we will discuss the trade winds. Trade winds are steady easterly winds that blow from subtropical high pressure belts toward the equatorial low pressure regions. When the sun shines, it warms certain areas more and the air there rises, creating a low pressure zone. Other air swoops in to fill this cozy spot, forming the trade winds. They blow steadily from east to west, spreading comfort across ocean and skies. Sailors in the past used these dependable winds for trading journeys, which is how they got their name trade winds. Now we will discuss the prevailing westerlies. These are prevailing winds that blow from the west in the middle latitudes between the subtropical high pressure belts and the subpolar low pressure belts. Prevailing westerlies are like the Earth's middle latitude winds that blow in a friendly west to east direction. They occur between the polar easterlies to the north and the trade winds to the south. These winds are a result of the Earth's rotation, which makes them veer from the west to east. Think of them as the gentle, reliable winds that shape weather in many parts of the world. Prevailing westerlies influence our climate, help with air travel routes, and play a role in moving weather systems, making them an important part of our atmospheric story. Next is polar easterlies. Polar easterlies are cold winds that blow from the polar high pressure belts toward the subpolar low pressure belts. Polar easterlies are like chilly, brisk winds that blow near the Earth's poles. These winds originate from the cold polar regions and head towards lower latitudes. They get their name because They blow from the east to the west, opposite to the prevailing westerlies. Polar easterlies are a result of the frigid polar air sinking and creating high pressure zones near the poles. These winds play a vital role in shaping our climate, especially in the polar regions where they bring cold, wintry conditions. They also help distribute cold air from the poles toward the middle latitudes, affecting weather patterns worldwide. Next is local wind systems. Local wind systems are influenced by local geographical features, temperature differences, and pressure gradients. These include first one is sea breezes, second is land breezes, third is mountain and valley breezes. Now we will discuss it one by one. Sea breezes. Sea breezes occur during the day when the land heats up faster than the adjacent water. The cool air from the sea flows inland to replace the rising warm air over the land. Second is land bridges. Land bridges occur at night when the land cools down faster than the water. Cooler air from the land moves towards the warmer water, creating a breeze. Next one is mountain and valley bridges. During the day, mountain bridges occur as cool air descends from the mountains to replace the rising warm air over the valleys. At night, valley bridges occur as cool air descends from the valleys to replace the rising warm air over the mountains. There are some other types of wind. First is the monsoon wind. Monsoon winds are seasonal wind patterns that bring heavy rainfalls to certain regions. They occur due to temperature differences between the land and sea. In summer, warm, moist air from the ocean moves inland, bringing wet weather. Next is katabatic wind. Katabatic winds, also known as drainage winds, occur when cold, dense air flows down a slope or hill due to gravity. Next is tropical cyclones and hurricanes. Tropical cyclones, also known as hurricanes or typhoons depending on the region, are intense circular storms characterized by strong winds, heavy rainfall and low atmospheric pressure. Next is jet stream. The jet stream is a high-speed, narrow air current in the upper atmosphere. It flows from west to east and influences weather patterns and air travel routes. Wind in its various forms and patterns significantly impacts the Earth's weather, climate, and nature phenomena. Understanding the different types of wind is crucial for a wide range of applications, from predicting weather events and planning renewable energy projects to facilitating safe navigation and preserving ecosystems. It is a testament to the complexity and diversity of our natural environment and underscores the importance of continued research and awareness about this dynamic atmospheric phenomena. Now we will discuss the meteorological parameters of the wind. Meteorological parameters of wind encompasses various elements that aid in understanding and measuring the characteristics and the behavior of wind. Wind, a critical meteorological factor, profoundly influences weather patterns, atmospheric circulation, energy production, and a wide array of natural processes. In this essay, we will explore key meteorological parameters used to analyze wind behavior and its implications. Wind speed is a fundamental meteorological parameter that quantifies the velocity of air movement. It is typically measured in meter per second or miles per hour. Accurate wind speed measures help in forecasting weather, predicting potential damage from strong winds, and optimizing wind energy production. Now, wind direction. Wind direction indicates the origin from which the wind is blowing and is expressed in degrees, usually relative to true north. Understanding wind direction is crucial for various applications including aviation, navigation and urban planning. Next is wind gust. Wind gusts are short bursts of high wind speed that occur within a short period. Gusts can significantly impact activities like sailing, aviation, and outdoor events. Meteorologists measure gusts to provide more comprehensive wind information for public safety and planning purposes. Next is wind variability. Wind variability refers to fluctuations in wind speed and direction over a given time period. Understanding wind variability is essentially for designing structures, assessing wind related risks, and optimizing wind energy installation. Next is wind shear. Wind shear is the rate at which wind speed or direction changes with altitude. It is crucial for aviation safety, particularly during takeoff and landing. Several wind shear can result in hazardous conditions for aircraft. Next is anemometer. An anemometer is a device used to measure wind speed and can come in various types such as cup anemometer, vane anemometer, and sonic anemometer. Cup anemometers have rotating cups that measures wind speed while vane anemometers determine wind directions. Next is weather vanes. Weather vanes, also known as wind vanes, are instruments used to measure wind direction. They consist of an arrow or pointed attached to a fixed vertical rod which aligns with the direction of the wind. Next is Beaufort scale. The Beaufort scale is a measure used to estimate wind speed based on observed sea conditions. It categorizes wind into various levels, helping sailors and meteorologists describe wind intensity and effects on the sea. Next is wind roses. Wind roses are graphical representations of wind speed and direction data over a specific time period. They are useful in analyzing long-term wind patterns and designing structures or planning activities accordingly. A wind rose diagram is a graphical tool used to represent the frequency and distribution of wind directions at a specific location over a defined period of time. It provides valuable information about the prevailing wind patterns, helping various stakeholders such as meteorologists, climatologists, architects, urban planners, and renewable energy developers understand local wind characteristics. Next is turbulence. Wind turbulence refers to irregular movements that can affect aircraft, especially during flights. Understanding and predicting turbulence is vital for ensuring passenger safety and a smoother flight experience. It may reduce by proper guidance and safety precaution. Now, wake effect in wind energy. The wake effect in wind energy refers to the phenomena where wind turbines create areas of reduced wind speed and altered wind direction downstream of the rotor. This effect occurs as the rotating blades of a wind turbine interact with the surrounding air, causing turbulence and energy extraction from the wind flow. Now, meteorological parameters of wind play a pivot role in understanding the behavior and impact of wind on various aspects of our lives. Accurate measurements and analysis of wind speed, direction, variability, and other parameters are crucial for activities ranging from aviation and navigation for renewable energy production and urban planning. Next is wind power density and its importance. Wind power density is the amount of power available in a unit area of wind. Wind power density varies with wind speed and altitude. Wind power density is a fundamental concept in wind energy that quantifies the amount of energy available in the wind at a specific location. It is a crucial parameter used to assess the potential for wind energy generation in a particular area. Understanding wind power density and its derivation is essential for optimizing the placement and efficiency of wind turbines and maximizing renewable energy production. Now we will discuss the formula of wind power density. The wind power density is a measure of power available in the wind and is derived from the kinetic energy of the moving air. The formula for calculating wind power density is based on the kinetic energy per unit volume of air. The derivation involves several steps. First one is kinetic energy of the wind. Kinetic energy is given by 1 by 2 into mass of air into velocity square. Therefore, the kinetic energy of the wind can be written as kinetic energy equals to 1 by 2 rho A d into v raised to 2. Now we will discuss power in the wind. Power is the rate at which energy is transferred or transformed. The power in the wind is given by the rate at which kinetic energy is being transported by the wind. So the power is kinetic energy per unit time, which can be written as power equals to kinetic energy into wind speed. Substituting the expression for kinetic energy, we get power equals to 1 by 2 into rho into A into d into v raised to 3. Now we will see the importance of wind power density. Wind power density is a crucial parameter in the wind energy assessment for various reasons. First one is site selection for wind farms. Wind power density helps in identifying locations with high wind energy potential, aiding in the selection of optimal sites for wind farms. Higher wind power density implies more energy can be harnessed from the wind at that location. Next is optimizing wind turbine placement. Understanding wind power density helps in optimizing the placement of wind turbines within a wind farm to maximize energy production. Next is project feasibility and investment decisions. Wind power density assessment are critical for evaluating the feasibility of a wind energy project and making informed investment decisions. Wind power density is a key parameter that quantifies the available energy in the wind and is vital for assessing the potential of wind energy at a specific location. Now we will discuss wind velocity duration curve. The wind velocity duration curve is a graph that shows the frequency distribution of wind speed over a period of time, or a wind velocity duration curve is a graph that shows the probability distribution of wind speed over a given period. The curve shows the cumulative frequency of wind speeds and is typically displayed on a logarithmic scale. This curve provides valuable information on the wind resource available at a specific site. First we will discuss the cut-in speed. The cut-in speed refers to the minimum wind speed at which a wind turbine begins to generate electricity effectively. Below this speed, the turbine blades are unable to harness enough wind energy to produce electricity efficiently. Typically, the cut-in speed for modern wind turbines ranges between 3 to 4 meters per second, or approximately 7 to 9 miles per hour. When wind speeds are below the cut-in speed, the turbine may not rotate or generate power at all. Next is cutout speed. Cutout speeds typically range from 25 to 30 meters per second, but they can vary depending on the design and manufacture of the turbine. The last is rated speed. The rated speed of a wind turbine is the wind speed at which the turbine generates its maximum rated power output efficiently. The rated speed varies depending on the design and size of the turbine. It's usually around 12 to 15 meters per second. Understanding these wind parameters is essential for wind turbine operators and designers to optimize performance, ensure safety, and maximize energy production from the wind resource. Now, energy pattern factor. It is a measure of the variability of wind speed over time. It is used to estimate the amount of energy that can be extracted from the wind. It is a measure of the variability of wind energy production over the time. and calculated by dividing the standard deviation of the power output by the average power output. Another important factor is wind power duration characteristics. The wind power duration characteristics are the statistical distribution of power over a period of time. The wind power duration characteristics provides information on the variation in wind power over time. These characteristics can be classified into three categories: short-term, medium-term and long-term characteristics. There are several key factors that contribute to wind power duration characteristics, including the wind velocity, the wind direction, and the wind frequency and duration of wind events. If we talk about the application and historical background of wind energy system, it is currently used to generate electricity, pumping water, and for other mechanical applications. The first wind turbines used to generate electricity were installed in Denmark in the 1970s. Since then, the technology has advanced significantly and wind turbines have become larger, more efficient and more cost effective. Some major benefits of wind energy include being a renewable source of energy, producing no emissions and having low cost of production. Wind energy offers several benefits and advantages, making it an increasingly attractive option for electricity generation. Here are some key advantages of wind energy. First one is it is a renewable and sustainable source. Second is clean and environmentally friendly. Third is energy independence and security. Next is abundant resource. Fifth one is cost competitive. Next is job creation and economic development. Next is scalability and flexibility. And the last is technological innovation and research applications. Some limitations of wind energy include it is land and visual impact, noise and aesthetic concerns. Next is bird and bat collisions, infrastructure and transmission constraints, and initial capital cost is high. Despite these limitations, wind energy remains a valuable and increasingly competitive renewable energy option, contributing to decarbonization efforts, energy security, and sustainable development goals worldwide. Addressing these challenges through technological innovation, policy support, and community engagement can help unlock the full potential of wind power as a clean and reliable energy source for the future. At last, we will discuss the future of wind energy. The future of wind energy holds significant promise and potential as countries worldwide continue to transition towards low carbon and sustainable energy systems. Several trends and developments are shaping the future trajectory of wind energy. First one is continued cost reduction. Second, offshore wind expansion. Third is hybrid wind projects. Fourth is grid integration and energy storage. Fifth is digitalization and data analytics. And the last is policy support and market incentives. Overall, the future of wind energy is characterized by innovation, scalability, and sustainability, with wind power poised to play a central role in transition to a clean energy future. As countries strive to achieve their climate goals, reduce greenhouse gas emissions, and enhance energy security, wind energy will continue to emerge as a key pillar of the global energy mix and social progress. In the next lecture, we will explore the construction and working of wind turbines. Thank you.